Welcome, everyone. We're about to do something most teams talk about but few actually achieve. Stop repeat failures for good. In this session, I'll walk you through a global 8D problem-solving sprint the way automotive expects it to be done. Evidence-based, fast, and permanent. By the end of 15 minutes, you'll have 3 powerful tools. A clean point checklist showing where to draw the line between good and suspect stock, a root cause test pack that turns opinions into evidence, and a Poka-yoke first playbook that reduces escapes by double-digit percentages. We're talking real impact. Cutting parts per million escape rates by 30% or more, slashing complaint counts, and saving thousands in cost of poor quality. If you stay with me to the end, and you will, you'll see exactly how your team can get those results and why you'll never go back to just filling out forms. In the automotive world, problem solving isn't optional, it's mandatory. When a defect escapes, the true cost isn't just the non-conforming part. It could be premium freight to airship, replacement parts, sorting and rework that kills capacity, line-down penalties that blow up the customer's P&L, warranty claims that drag on for years, and perhaps worst of all, the long-term hit to trust. One avoidable escape can erase a quarter's worth of profit. That's why OEMs demand evidence-driven 8D analyses. It's a common language to protect the customer, fix problems permanently, and drive systemic improvement. Here's our roadmap. D0 is emergency response. Triage, protect the customer, and declare a clean point within 24 hours. D1 assembles a cross-functional team and sets a daily cadence. D2 turns noise into data with a measurable problem statement, an IS/ISNOT analysis, and a quick measurement system analysis. D3 establishes customer protection, quarantine suspect parts, verify containment, and set up a firewall. D4 digs into root cause and escape with tools like 5Y, Ishikawa, and cause tests. D5 selects permanent corrective actions, Poka-yoke first, covering all root causes. D6 implements and validates those actions with both quick checks and long-term capability studies. D7 prevents recurrence by updating standards, rolling changes to similar products, and building the lessons into layered process audits. Finally, D8 closes with evidence, approval, and celebration. In automotive, this sprint generally follows the 1-5-20 rule. Contain within a day, find and agree the root cause within 5 days, and prove the fix within 20 days. Picture this. You're deep in your day when the phone buzzes. Customer says, "Our line is down, your bracket won't fit." Your heart sinks. 3 months ago, you chased a similar whole-size issue. You thought it was resolved. The clock is ticking. Every minute of downtime costs thousands. If you do nothing, you could lose the customer and lots of money. In this moment, you need more than a guess. You need a structured response that protects them immediately and prevents it ever happening again. The fire you feel right now is the fuel for learning. We'll channel it into a methodical sprint. The goal of D0 is simple. Protect the customer and put out the fire. Immediately decide whether to stop shipments or launch 100% sorting or rework. Open a visible log with times, quantities, and owners. Within hours, declare your clean point, a lot number or timestamp after which every part shipped is verified good. Important thing is that, don't guess. Include evidence such as inspection records, lot IDs, and photos. Communicate your containment plan and clean point to the customer through their portal. Use data to reassure them. Share how many suspect parts were quarantined, how you verified the firewall with run charts, and what's being done upstream. A clear, data-backed clean point calms the customer and buys you time to do real analysis. D1 is about people and communication. Assemble a cross-functional team. Process, quality, maintenance, tooling, logistics, and sometimes supplier quality. The key point is that creating team with a multidiscipliner people. Make sure each member has the skills to analyze the root cause, define and implement corrective actions, and monitor their effectiveness. Appoint a team leader experienced with the 8D process, and a sponsor or champion who can remove roadblocks. Establish a daily cadence for internal stand-ups, and set a single voice to the customer portal. No mixed messages. Ground rules like meeting discipline, escalation process, and record keeping set the team up for a smooth sprint. Now let's convert frustration into data. Be careful while performing D2 section. It is important to clearly define the problem you are facing in order to resolve it correctly. Write the problem as a quantified statement: defect, object, location, timing, and extent. Include the customer report, the failure effect, the exact specification deviation, defect location, and production details. Then build an is and is not grid, where and when the defect is found, and, equally important, where it is not. This eliminates random guesswork and highlights the most likely root causes. Use the 5W1H method to gather all relevant facts. What object has the problem, when it was observed, where it occurs, who or which qualifications are involved, whether there's a trend, and how the deviation manifests. Collect data and facts: production date, shift, batch, measurement results, and reject rates. Next, verify that the data you're using is reliable. Perform a quick measurement system analysis or gauge R&R check. If your measurement variation is over 30%, the system is unacceptable. Between 10 and 30% is conditional, and below 10% is preferred. This quick step 2 prevents you from building an 8D on noisy data. Finally, set your targets clearly. Without a defined specification and acceptable performance criteria, teams will debate opinions instead of facts. Tie the problem statement back to a customer requirement or spec limit. That way, success is clearly defined when you select corrective actions. D3 builds a firewall while root cause work proceeds. Containment actions protect the customer by isolating the problem from the entire supply chain and avoiding delivery or assembly of suspect parts. Actions can include 100% inspection, sorting checks, or rework. Define responsibility and start dates for each containment action. Monitor status and assess risks, because containment itself can introduce side effects. Verify effectiveness with data. Use run charts or additional gauge checks to monitor defect rates and confirm that no further bad parts reach the customer. Clearly mark dirty and clean areas so employees don't mix suspect and verified material. Remember, the firewall stays up until you've validated the permanent corrective action in D6. D4 is the heart of the 8D. Root cause analysis must consider 3 levels: the technical root cause, why the defect occurs; the quality assurance or escape cause, why it isn't detected; and the systemic or development root cause, why the system doesn't prevent it. Neglect any of these and the problem will return. To ensure completeness, use the 3-legged 5. Why? Perform a separate 5. Why on each leg: occurrence, escape, and systemic. Start brainstorming possible causes using Ishikawa or Fishbone diagrams when the cause is unknown or complex. Categorize potential causes across men, machine, material, method, measurement, and environment. Then use 5 why to drill down, remembering that 5 is just a rule of thumb. The root cause might emerge after 3 questions or 7, so do not fix yourself for 5. Dig it until you find the cause. Next, apply a cause test for each possible cause you find. Does it fully explain the data, partially explain it, or not explain it at all? Eliminate causes that don't match. For ambiguous ones, do further investigation. When multiple interacting factors are suspected, use fault tree analysis. Most importantly, verify every proposed root cause. The root cause must be something you can turn on or off at will. Reproduce the defect by manipulating the suspected cause. Confirm the defect disappears when the cause is removed. Only when both occurrence and escape causes are proven with data do you proceed to D5. In D5, you choose actions that will permanently remove the causes you've verified. Start by listing potential corrective actions covering all root causes. Verify and evaluate each one. Perform a risk analysis. Weigh the advantages and disadvantages and be careful of unintended side effects. Establish acceptance criteria and use tools like FMEA to assess risks. Prioritize poke-a-yoke, error proofing that makes the defect impossible, over additional inspection. For the occurrence leg, consider sensors, 3 interlocks, or automation to prevent misassembly. For the escape leg, improve detection by upgrading gauge sensitivity or increasing sampling. For the systemic leg, update design guidelines or maintenance plans. Choose the simplest, most cost-effective solution that covers all root causes. Don't forget the human side. update training materials, work instructions, FMEA, and control plans, so the new process is documented and auditable. Employees must understand the new standard. Simply posting a notice isn't enough. Refresh training for operators, quality inspectors, and maintenance teams if needed. And remember the cost of quality. Investing in prevention may have a cost up front, but it reduces warranty expenses and complaint handling later. Corrective actions must address the root cause, the escape cause, and any systemic weaknesses. With the right actions, you'll often see complaint rates drop by 30% or more. D6 answers the question, do the actions work? Begin with a documented implementation plan that assigns responsibilities and dates. After installation, run a quick check, a provocation test, to deliberately challenge the new control and show that it catches or prevents the defect. For example, intentionally introduce an undersized drill bit and confirm the interlock stops production. This immediate test verifies that the new POCA yoke or detection control behaves as intended. Then run a long-term check. Collect data under normal conditions and evaluate process capability. Look at your CP and CPK values, failure rates, and product audits. Only if the process is both stable and capable, you can remove containment. Simulation matters too. Perform rabbit part audits or golden part verifications by running known good and bad parts through the system to ensure it discriminates reliably. Conduct both product audits, dimensional checks, functional tests, and process audits. Confirm procedures are followed, gauges are calibrated, checklists are complete. If validation exposes gaps, return to D5 and refine your actions. Many repeat failures occur because teams skip rigorous validation. Don't let that happen. D7 ensures the fix spreads and stays. Start by updating relevant documents, drawings, FMEA, control plans, maintenance plans, and standard work. Extend the changes to similar products and processes through Yokoten. Read across. Ask where else this issue could occur, and implement the same controls proactively. Set up or refresh layered internal management and the customer. Many OEMs require a plant or quality manager to sign off. Archive the supporting data and update the portal status to closed or accepted. Then recognize the team. Publicly acknowledge the cross-functional effort, share customer feedback, and celebrate the success. Recognition reinforces the behaviors you want to see again. Different customers use different portals, but patterns repeat. Ford's portals emphasize a clear evidence trail and feeding lessons learned into future projects. Ford used Covisint and FOSN portals to follow claims. GM's portal requires a rapid cadence of updates and emphasizes data and next steps. GM use Supply Power/PRR portal. Stellantis demands logic chains and proof of standardization and use SQP portal. Volkswagen, Audi use KPMQS and they looks for evidence of standardization. Mercedes wants detailed governance and use QEC tool. BMW and Toyota have their own forms. BMW use QMT portal and Toyota use SQAM portal. Tesla use SCAR portal as well. Regardless of portal, suppliers should follow the 1-5-20 rule. Within 1 day, define and communicate containment actions. Within 5 days, submit root cause analysis and corrective actions. Within 20 days, prove the fix and communicate actions to prevent recurrence. All portals want concise notes, time-stamped updates, and attachments like gauge studies, cause tests, corrective action verification data, and capability charts. They reward clarity and penalize vagueness. Understanding each customer's focus lets you tailor your reports and build confidence. Let's ground all of this in a realistic case. Suppose the target hole diameter is 10.00 millimeters plus or minus 0.05. The customer reports 8% of parts arriving between 9.86 and 9.89 millimeters. Their line stops. You trigger D0, stop shipping, segregate suspect parts, implement 100% inspection, and declare a clean point at 1425 on September 5th. Lot B271. You record quantities, inspection methods, and attach the log. In D1, you assemble your cross-functional team with process, quality, maintenance, tooling, logistics, and a sponsor. you set a daily update time with the customer. During D2, you write a measurable statement and build your IS/ISNOT grid. The problem occurs on line B, operation 20, heat lots H12 and H13, mostly on shift B near the end of tool life. It does not occur on line A, shift A, early tool life or heat lots H10 and H11. You verify the gauge, bias acceptable, linearity marginal at the lower spec, and collect data on coolant concentration, tool cycles, and hardness. You set a target CPK of 1.33 or higher. In D3, you install a temporary pin gauge station with tightened sampling at the end of the operation and mark separate dirty and clean zones. You run a false negative challenge and record 0 escapes during containment. For D4, you generate hypotheses: coolant drift, tool wear, fixture mislocation, gauge bias, material hardness. You run titration tests and plot coolant concentration versus defect rate. Shift B shows a drop to 4.8% just before the defect appears. You analyze tool life and see the diameter trending down near end of life. Fixture repeatability is clean, hardness normal. Gauge linearity is marginal but not the root cause. You intentionally run the tool past its life and lower coolant concentration. The hole goes undersized. Raising coolant and resetting tool size eliminates it. You conclude the occurrence causes are combined coolant drift and tool wear. The escape cause is an insensitive gauge and sampling gap. The systemic cause is missing control in the design and maintenance system. In D5, you select permanent actions. Install an automatic coolant mixer with low-level interlock and daily titration checklist. Add a tool life counter with and-on and interlock. Replace the gauge with a more sensitive digital indicator and revise sampling frequency. And update the FMEA and control plan. You verify cost and side effects and train operators and maintenance on the new systems. In D6, you validate. A provocation test shows the interlock stops the machine when coolant is low or tool life is exceeded. SPC charts show stability after the fixes. Capability improves to CPK, greater than or equal to 1.33. Product audits confirm holes stay within tolerance. You remove containment with customer approval. In D7, you update drawings, FMEA, control plan and maintenance plans. Implement the same controls on line A and the sister plant. Add LPA questions and capture lessons learned. In D8, the customer accepts the report. You archive the data, issue a one-page lesson card, and thank the team. Implementing these controls not only solved the problem but improved process capability across similar parts, reducing PPM by more than 30% and slashing complaint calls. What happens when you execute a world-class 8D? You transform a crisis into an opportunity. Investing in prevention, measurement, and error-proofing reduces the cost of poor quality dramatically. In our case, the new controls cut escapes by over 30%, halved complaint calls, and paid for themselves through warranty savings. Team members learned new problem-solving skills, the company's reputation improved, and future products will benefit from the lessons learned. That's the real payoff. You don't just fix one defect, you build organizational muscle that makes tomorrow's problems easier to solve. Today we talked about how to use the 8D problem-solving approach to eliminate recurring failures and improve quality. We reviewed the core steps, key checklists, and the tools you'll need to drive continuous improvement. In our next training video, we'll take a closer look at each stage from D0 through D4. We'll show you step-by-step how to respond to emergencies, assemble your team, define the problem, and conduct root cause and escape analyses. By following this series, you'll be able to perform much more effective analysis in your own work and implement solutions that stick. If you'd like to see more content like this, please don't forget to like the video and subscribe to the channel. And if you have other topics or questions you'd like us to cover, please share them in the comments. See you in the next video.
Is it really possible to eliminate recurring defects for good? Today, we'll explore the industry-agnostic language of problem-solving, the 8D analysis, and walk it in one continuous flow from D0 to D4. Grab your coffee and water, settle in, and focus. By the end of this video, you'll know how to make the right analysis for the right problem. Your phone rings on the production line, your heart rate spikes, and you can hear the tension in the customer voice. Your brackets don't fit. If the words recurring defects make your stomach drop, this video is for you. Because today, we're going to speak the language that every OEM, from Audi to BMW, from Ford to Volkswagen, expects. By the end, you'll know how to define a clean point, how to sharpen the problem with an IS/ISNOT matrix, when to run MSA, how to turn your firewall into zero defect flow, and how to prove the occurrence cause, the escape cause, and why the quality system failed to catch it. All crystal clear. Let's stage the moment. On the customer's assembly line, the bracket that you supply won't fit. Minutes feel like seconds. The question in your head, is there any suspected stock already on the way, gets louder. This is where the first step of 8D kicks in. D0, the critical moment. D0, stop and protect. Picture it. It's 2:30 p.m. The customer calls. There's a bracket issue. What do you do in the first 60 seconds? Most people panic. You won't. Because now, you'll learn the inform and control reflex. The rule is non-negotiable. Customer line risk must drop to zero immediately. Stop shipments. Quarantine suspect stock. Start 100% sorting if necessary. But careful, here's the important point, the clean point. From this lot number onward, every part has been verified and is safe. Can you say that with evidence? Are your lot lists, photos, and data ready? What do we do? Review outgoing shipments, quarantine suspect stock, and, if needed, launch 100% sorting. With one crucial difference, we record everything minute by minute. Who did what, when, how many, and how. And then the critical detail. We declare the clean point. From this time, after this lot, serial number, every part has been verified and is safe. You must be able to say this backed by proof. Lot lists, inspection records, photos, and data ready to go. Then push the package as a time-stamped update in the OEM portal, or, if a formal complaint hasn't been opened yet, via email. Don't worry, in a moment, I'll tell you exactly what different OEMs expect here. With D0 underway, many teams are tempted to skip D1. Just don't. D1, don't fight alone. Build your team. Anyone who says, "I'll handle it myself," loses. Why? Because D0 to D3 actions move hourly. You can't keep up alone. And you can't be the expert in everything. In D1, build a cross-functional team. Production, quality, process engineering, maintenance, tooling fixtures, logistics, supplier quality. Bring in the customer represent if needed. Gather everyone who can help solve the problem. Appoint an 8D leader and a sponsor who removes roadblocks. Adopt the one-voice rule. One coherent message to the customer portal. Hold short daily stand-ups. Why? Because D0 to D3 actions evolve by the hour. As root cause hypotheses appear, ownership and priorities shift quickly. The purpose of D1 is to keep everyone on the same page with written roles and responsibilities. How should we actually define the problem? That's where D2 sets the game. D2, make the invisible visible. Ask, what is the problem? And everyone says something different. That ends now. D2's goal is to turn noise into clear, measurable information. First, write a quantifiable problem statement. What is the object? What is the defect? Where does it appear? When did it start? How widespread is it? For example, the shaft hole must be 10 plus or minus 0.1 millimeters. Oversize measurements drifting to 10.48 to 10.52 millimeters have been observed on line B during the night shift since the third week of February at a frequency of 4 to 5%. Anyone who reads it should picture the same thing. Then open the IS/ISNOT matrix. Where does it exist and where does it not? Which line? Which shift? Which material lot? Which alternate supplier? Which operator combination? In parallel, ask what changed? Shift, tooling, software, software, material, supplier, environment. This table dramatically narrows your hypothesis pool, and the accuracy of your later analysis and the relevance of your actions will hinge on doing it thoroughly. This matrix can narrow your hypothesis field by 90%. Now, a critical checkpoint, MSA. If you can't trust your measurement, the entire analysis collapses. Run a quick gauge R&R. As a rule of thumb, below 10% good, between 10 to 30% borderline, above 30% unacceptable. If your measurement system is weak, fix that first. Otherwise, you'll chase a phantom. Many repeated 8Ds trace back to a D2 written on unreliable measurements. You've covered the first 3 steps. Now, D3, the interim fix, the firewall. D3 is simple in logic and strict in discipline. Protect the customer behind a wall until you find and fix the root cause. This is where 100% inspection or sorting kicks in. Physically separate dirty versus clean areas. Add an extra inspection station at end of line if needed. Bring in third-party sorters when appropriate. But the lifeblood of D3 is this: proof that your added control works. We inspected is not enough. How many units did you check? How many defects did you find? Who did it and where? All signed and recorded. Stress test the firewall with a false negative challenge. Push a known bad part through the check. Does the system catch it? If not, your firewall is paper thin. Remember, in the OEM's eyes, D3 is often proven by a run chart trending to escapes equals 0. Now, D4, the heart of 8D. Here's the part everyone misses. Many teams declare victory after finding the occurrence cause. This is insanely wrong. In D4, you must work 3 separate legs: the occurrence, why it happened; the escape, why it wasn't caught; and why the quality system allowed it. Find occurrence only, and the same kind of defect will leak again if you don't close the escape or the system gap. Keep D4 sharp with 3 questions. Can I turn the root cause on and off? Why did our current control fail to catch it? And what in the quality system failed to prevent it? Never stop at operator error. Ask one level deeper. Why did the system allow it? How do we proceed? Start with a fishbone and brainstorm across 6M/7M categories: man, machine, method, material, measurement, environment, and management. Map the IS/ISNOT clues from D2 onto each branch. Then build 3 separate 5Y chains for occurrence, escape, and system. Don't stall on shallow answers. If it lands on a person, ask why the system let that happen. Then comes the critical phase: evidence-based validation of the causes you found. Deliberately turn the suspected cause on to reproduce the defect, then remove the cause and show the defect disappears. Suspect material, run parts with the suspect lot and collect data, then repeat with conforming material. Suspect a worn fixture, do measurements drift with a worn fixture, and stabilize with a renewed one. For escape, think experimentally too. Was gauge resolution inadequate? Was sampling frequency too low? Was the control plan measuring the wrong characteristic? When you add these tests, charts, and tables to your 8D, you've delivered proof of root cause. Moving to D5 without proof is leaving the door open to the wind. And remember, no one wants to relive the same failure on the line. In automotive, repeated issues are unacceptable and quickly escalate. Up to this point, we've built the skeleton of the analysis. The stronger one, the better the outcome. Now, what exactly do different OEMs expect at these steps? Most OEMs want a VDA-structured 8D submitted through their supplier portal. Timelines typically look like this: an interim update within 24 to 48 hours covering D0 through D3, then validated root cause analysis, D4, shared around day 5 to 7, and a final 8D within 10 to 30 working days, depending on complexity. On the Ford side, you'll often hear 1-5-20. Day 1, emergency response and containment. Day 5, interim root cause/plan. Day 20, final. BMW commonly expects the first response in 48 hours and a final report in 20 working days. For Volkswagen/Audi, within formal Q/KPM-QS, you should make the D0 to D3 progress visible visible in the portal within 24 to 48 hours. At Mercedes-Benz, through QEC, analysis/inspection outputs are expected from the point of part receipt. Priority cases may impose tighter timelines. Renault frequently promotes QRQC/A3 culture, but wants content equivalent to AD. Portals guide the steps and expect each field complete, often D0 to D3 within 24 hours, and D4 within a week. With Stellantis, Fiat, Peugeot, Opel, Citroën, you progress the 8D steps with portal approvals on consolidated platforms. Toyota often runs via A3 problem solving and expects 8D equivalent content. Hyundai Kia supplier quality guides mirror an 8D-like flow with fast initial notification expectations. Now, let's get practical. Here's a 7-step success formula you can win with on your very next case. 1. Within the first 24 hours, prove the clean point with measurements and records. Share numeric updates through the portal. From this timestamp onward, we have defect-free flow. Products are usable, starting with shipment X. We inspected N parts, found K defects, and launched these actions. 2. Build your team. With the one voice principle, post at least one portal update per day. 3. Define the problem with an IS/ISNOT matrix. Where does it exist? Where not? When did it start? What changed? Show this table to the customer, and it signals you're on target. 4. Run MSA early. If GR and R is poor, your first fix isn't the root cause, it's the measurement system. Then, rerun your matrices and review findings. 5. Strengthen the firewall with records. Total inspected, defects found, who where, plus a false negative challenge. Upload a run chart trending escapes equals 0. 6. In D4, work the 3 legs: occurrence, escape, and system. Build 3-legged 5 whys. Then, plan and execute on-off experiments. Unverified hypotheses do not belong in the report. 7. Compile all evidence in the format your customer requires, in short, sharp sentences. A good 8D isn't only correct, it persuades by showing proof. Why are we so obsessed with evidence? Because in automotive, the phrase, "we think that," is a cost item. Evidence is the only way to tell the customer, we've contained the issue, found the root, and improved the system so it won't happen again. D0's clean point, D3's firewall effectiveness, D4's on-off tests, they all send the same message. This team's word is backed by data. They're professional, and they can solve the problem for good. If you tailor this flow to your plant's language and your customer portal's rules, you won't just fill in an AD, you'll systematically build trust with your customer. That trust makes collaboration easier and keeps you away from escalation paths nobody wants. In the next training video, we'll cover D5 to D8, how to select permanent corrective actions, verify them, and strengthen the system for good. But first, put these 3 into practice now. Clean point evidence, IS/ISNOT plus MSA, and on/off test plans for occurrence, escape, and system. These are the game-winning moves in the first half of your 8D. Before you go, if you found this helpful, please like the video and share it with your team. Subscribe and turn on notifications so you don't miss future content. Tell me in the comments what you want to see next. Until the next video, take care, and let's keep those defects from coming back.
You had said, we solved the problem. You sent the 8D report the customer expected, and you restarted the normal shipment order. But 3 months later, that phone rings again. Same customer, same error, same part, same nightmare. And this time, the conditions are much heavier. Customer trust is 0. The manageability of the problem is at an impossible point. The most dangerous misconception in the automotive world is to think we solved the problem. If you only applied a Band-Aid, it means that error returning is inevitable. I am Halil Ibrahim, a mechanical engineer and manager in the global automotive sector. Today, we are breaking this recurring error cycle forever. Grab your tea, your coffee, sit back and collect your focus here. Because just finding the root cause is not enough. We are in the final episode of our 8D series, where we will see how you will solve that cause on the field and how you will guarantee your system. In D5, we will choose the best moves. In D6, we will prove them on the field. In D7, we will take the future under protection. And in D8, we will close that file with success, never to be opened again. How is a professional 8D finished? If you are ready, let's get in our vehicle and go on a journey towards the inside of the real operation. Now let's remember how we got here. With D0, we gave our first reaction, we extinguished the fire and protected the customer. In D1, we gathered the right team. In D2, we defined the problem with data. We turned noise into information. In D3, we wove our security wall with interim measures. And in D4, we proved those famous root causes with a forensic meticulousness. Let's return to our case. Our target was a 10 plus or minus 0.1 millimeter perfect shaft hole, but our parts had drifted down to 9.80 millimeters. Through the on/off tests we performed in the D4 step, we found the problems one by one. The occurrence root cause of the error was the uncontrolled deviation in the coolant concentration and the tool life having come to an end. Escape cause was that our measurement system remained too sluggish to catch these small deviations. Our system root cause was the absence of any measures for this wear in the maintenance and design instructions. We didn't just guess the root causes, we validated them in the production. Our D4 step is finished, we found the killers, but now we are at the most dangerous curve. Which of the dozens of solutions on the table will truly save us? D5 is the chessboard in automotive. We definitely have no luxury of making a wrong move here. Most teams just find one solution and immediately run to the process. Professionals, however, lay the options on the table. According to IATF 16949 Clause 10.2.3, professionals here lay the options on the table not only according to their cost, but also according to error-proofing strength and statistical confidence criteria. In our shaft hole case, you must close three separate legs: occurrence, escape, and system. For the occurrence root cause, we put the actions of an automatic coolant mixer to take the tool temperature under control and a locked life counter to track tool life on the table. Here, we are operating the poka-yoke philosophy. When the tool life is full, before producing an erroneous part, the machine will stop and demand that you change the tool. For escape, we made the decision to change that sluggish measuring device with a digital indicator with data output and high precision where we can see the deviations instantly. We must decouple the problem from operator initiative as much as possible. On the system side, we updated our maintenance and design standards that allowed this error in the design phase. Now, while commissioning a new tool, our standards will automatically demand these actions. But stop, just finding the actions isn't enough. You must also do a risk analysis for the new situation. The critical question we must ask is this: do the solutions we found break somewhere else while fixing something? For example, is there a new failure risk of the automatic system we installed? You must reopen your FMEA file and weigh the side effects of each permanent corrective action you chose with a forensic meticulousness. Do not just lower the scoring. Question whether a new failure mode has been born in VDA standards. Finally, before making big investments in the process, verification is a must. Before spreading the new systems to the whole factory, we established them as a pilot in the problematic line and did trials. With the results on paper and small-scale trial results, we confirmed that our actions worked effectively, meaning the theory held in the field. We know that this new system will truly protect us when we remove the interim measures. Now, we are ready to spread the operation to the field and do validation. That is the D6 step. With the green light we received from the pilot area, we are now at the time of doing validation in the field. The D6 step is not just an assembly phase, it is a documentation discipline. According to IATF 16949 Clause 10.2.3, you must proceed through an implementation plan where the person responsible and the completion date of each action are recorded. Now that automatic mixer is in use, the locked life counter is active, and those sensitive digital indicators have taken their place right in front of the operator. We are at the time of measuring the effectiveness of the actions we took, that is, the effectiveness control expected by automotive. In this phase, the greatest pressure is the question of when the security wall we added in step D3, which has been reducing the company's profitability for a long time, will be removed. As a professional manager, you should neither rush nor act slowly and use labor incorrectly with unnecessary controls. When permanent actions descend to the field, your first task should be to update the standard work instructions, SIT, and on-the-job trainings, OJT. You cannot tear down that wall before all employees fully internalize the new standard. The first place a VDA 6.3 auditor will look when they knock on your door is here. Did the actions descend to the field, and did the employees turn this into a reflex? Just installing the equipment is not enough. You must be sure that every single operator on the field has adopted and applied the new standards. The eyes of the OEMs are on you. Ford's 20 working day rule is ticking. You cannot just write "we did it" to Ford's FOSN, Volkswagen's KPM-QS, or GM's supply power systems. We record the technical evidences on the field, the training records, and our new standards that say this error can no longer occur here, and update the customer portals. But remember, just as acting slowly to remove interim measures is a mistake, rushing is also a very big mistake. We only need one thing to remove unnecessary controls: real validation data coming from the field. We put the actions into use in the field. However, the automotive world doesn't look at you saying, "I did it." It always looks at you proving it. We start the validation process, which is the heart of D6, by manipulating the system. In professional language, we call this a provocation test, or rabbit part audit. What exactly did we do in our case? We attached a deliberately worn tool to the system system or set the tool life counter to end of life on purpose and observed the reaction of the system. The technological armor we designed, that is, that level 3 Poka-yoke system, must catch the error at the moment it is born and lock the bench instantly. If the system says stop to this provocation, it means you have crossed the first big hurdle. However, provocation testing alone is not enough. The automotive sector expects a statistical stability from us. According to IATF standards, you have to measure the capability and performance of the new process with concrete data. In our case, we gathered serial production data of at least 30 to 50 parts and created our SPC charts. If our CPK value is above the 1.33 value or even above the 1.67 value, according to special customer requests, we will have statistically proven that our process is now not only correct, but at the same time stable and reliable. The moment you take this validation data in your hand, we can safely remove that tired security wall, maybe for months reducing the company's profitability. That is 100% manual control. But remember, you cannot just write "the problem is over" to close this step in OEM systems like Ford's FOSN portal or Volkswagen's KPM-QS. You must upload the records of the provocation test, statistical capability reports, and up-to-date audit results on the field to the customer portal as an evidence pack. Now we are moving to the most critical phase for this success to be permanent and standardized in all similar operations: intervention in the DNA of the error, that is, the D7 dissemination step. We successfully destroyed the problem on line A, but for a professional manager, this is not enough. According to IATF standards, now you must make the most critical and highest scoring move: Yokoten dissemination. We have to ask this question: is the risk only in this machine, or are our other lines with similar technology, even our sister factories in different countries, facing this silent killer? We are spreading the automatic mixer and tool life counter solution, in our case, to all operations carrying potential risk as a corporate standard. OEMs like Volkswagen and Audi Group will demand precisely the geographical and technical evidence of this dissemination from you over their own portals. The D7 step is where we intervene in the DNA of the error and build the documentation fortress. In automotive discipline, just attaching a part to the machine is not considered a permanent solution. You must engrave this bitter experience into corporate memory. We lower the occurrence and detectability risk scores of the relevant failure mode in your FMEA file with data and revise your control plan according to the new digital measurement precision. The technical expectation of Ford, Toyota, Renault, and many OEMs is clear here. Did you transfer the lessons you learned from this error as a design rule to your future projects that are still in the design phase? Now, while a new project is being commissioned in your factory, your design standards will demand these actions automatically at the very beginning. What I mean is, the lessons learned, that is, the file of acquired experiences, being turned into a living organism. But the deepest question is still on the table. Why did our management system allow this error in the design or planning phase? We descend to the most crucial point of our three-legged analysis, that is, the systemic root cause leg. If there is no control item for toolware in your maintenance plan, or if your purchasing specifications do not mandate the automatic mixer system, this is a serious management system gap. This is the real answer Mercedes-Benz looks for in QEC audits or BMW looks for in the QMT portal. How did you close the systemic gap, not the operator error? You should take the acquired experience file off the dusty shelves and make it a living guide and an inseparable part of the APQP process, that is, new product commissioning. Remember, experiencing an error once is experience, but allowing the same error to be reborn in a new project is a systemic failure. The 8D process does not end the moment you send the report to the customer. It ends the moment that report is accepted as forensic evidence. D8 is the final of the 20th day in that famous 1-5-20 rule in the automotive world. In Ford's FOSN portal, in Volkswagen's KPM-QS system, or on Mercedes's QEC screen, or in Tesla's SCAR portal, the operation continues until you see that accepted statement. Many OEMs mandate that the report be officially approved not only by an engineer, but by the factory manager or quality manager at this stage. Even though 8D reporting is an industrial standard in the automotive world, every OEM manages this process over their own digital ecosystem with their own unique technical priorities. Ford, through FOSN and Covasint portals, gives critical importance to evidence traceability and the transfer of learned lessons to future projects. GM expects a data-oriented, extremely fast update tempo via supply power, while Stellantis looks for a flawless logical chain and proof of standardization in Amadeus and SQP portals. Volkswagen and Audi Group demand full compliance with VDA standards and technical dissemination proof in the KPM-QS system. Mercedes-Benz questions detailed governance and analysis outputs with the QEC tool. BMW QMT and Toyota offer a structure that blends A3 methodology with 8D content with SQAM portals. Tesla follows all these critical processes via the SCAR portal and displays a discipline that expects rapid notification and full compliance with the 8D flow like Hyundai and Kia. The trace you leave behind while closing your file is the signature of your professionalism. Do not just put a form in your archive, leave a complete evidence pack containing MSA data, on/off tests proving the root cause, those famous provocation videos, and statistical capability tables. One day, when an IATF auditor knocks on your door, you will not just say to them, "We solved the problem." You will lay this pack on the table and say, "Here is the proof." 8D is not a one-man show. It is a multidisciplinary teamwork. In D8, you must definitely appreciate the quality specialist chasing the 10.00 millimeters shaft hole in those sleepless nights, the maintenance person who installed the automatic mixer, and the operator who strictly obeys the new standard. Appreciating the success of the team, that is, recognizing them, is the strongest fuel employees need in the next crisis. And most importantly, the cooling liquid and toolware lesson, in our case, being turned into a one-page lessons learned card and spreading to all cells of the factory. We have come to the end of our 8D series for now. Tomorrow morning, when you go to work, go across that most annoying error in your field and ask yourself these 3 questions. Is this a Band-Aid or a surgery? Where is my evidence? And has the system's DNA really changed? If your answer is a Band-Aid, without waiting for the phone to ring again, gather your team and restart the operation. Do not just write the standards, live them on the field. I am Halil Ibrahim. For this and many educational videos and technical content like this, you can follow my channel, like my videos, and share them with your friends. Until we meet in the next operation, take care of yourself and stay safe.
Hi everyone, I'm Halil. Today I'm joined by Chris and Jane. We're tackling a critical topic in the automotive world, problem-solving approaches, better known as the 8D method. Born in the 1980s on Ford's shop floors as team-oriented problem-solving, it evolved into what we now call the 8D process. From aerospace to automotive, from medical to defense, it's become the standard. In this episode, we'll break it down fast and make it actionable through the lens of real automotive practice. Chris, over to you.
Okay, let's dive deep into global 8D problem solving today. It's really the core language for quality in the automotive world.
Absolutely. And the stakes are just massive. People sometimes forget the real cost of a quality escape. It's not just the bad part.
Oh, definitely not. You're talking premium freight, maybe huge line stoppage penalties from the OEM, warranty claims down the line.
And the damage to customer trust, that's hard to quantify, but it's incredibly significant.
Right, so ADD is meant to fix that, right? Not just patch the problem.
Exactly. The whole mission of 8D really is to push organizations away from just, reacting to symptoms. It's about getting to documented systemic prevention. That's what standards like IATF 16949 actually demand.
And there's that pressure, that timeline.
The 1-5-20 rule.
Yeah,
it forces discipline. Basically, you've got 24 hours for verified containment, then 5 days, just 5, to really nail down the root cause analysis. And finally, 20 days to get a permanent fix implemented and fully validated. It's intense.
A real measure of how fast your organization can react. So that first 24 hours, that's D0, the emergency response action, or ERA, that's just stop the bleeding.
Pure triage. Stop the bad parts from getting to the customer immediately. But the key deliverable, the thing the customer absolutely needs.
The clean point.
The clean point, you have to define it. This lot number, this production date, this timestamp, where you can guarantee 100% good parts are flowing again.
Okay, so containment's locked down. Then comes the heavy lifting D4, the analysis part.
This is where, honestly, a lot of 8Ds fall short. People tend to start too soon. They don't dig deep enough.
You mean like using the 5 whys?
Precisely.
Yeah.
The 5 whys technique, originally from Toyota, right? It's crucial for pushing past the easy answers. Everyone finds operator error as a cause initially.
Yeah, seems obvious sometimes.
But a really good investigation sees operator error and asks, okay, why did the operator make the error? Keep asking why. You usually find the real systemic cause is maybe 4 whys deeper. Things like inadequate maintenance procedures or unclear work instructions, or maybe training wasn't documented properly.
Okay, but hold on. The 8D standard asks for 2 root causes, doesn't it? In just 5 days. Why the escape point root cause, too, isn't fixing why it happened enough.
It feels like extra work under pressure, I get it. But think about it, the bad part being made is only half the problem. You need the occurrence root cause. Yeah, why the defect happened in the first place, but you also need the escape point root cause. Why did your quality system, your checks, your gauges, your audits, why did they fail to catch it before it left your facility?
Okay, so the system failed twice. Once in making it, once in detecting it.
Exactly, and if you only fix the making it part, your detection system is still flawed. The problem could easily happen again and escape again. You've got to fix both vulnerabilities.
That makes sense. which leads us right into D5 permanent corrective actions, or PCAs, if we're fixing the system.
Then the focus has to be on error proofing, or POPIO, making it physically impossible or, logically impossible for that specific error to happen again. Just adding another inspection step is usually the weakest response. We want prevention.
And then D6 is where you prove it actually worked. Validation.
Moment of truth. This isn't just crossing your fingers, you need hard data. Usually this means demonstrating process capability, like achieving a CPeak of 1.33 or even higher, to prove the fix is stable and effective.
Only then can you maybe remove some of those initial D0 containment actions.
Correct, once you have that statistical proof.
So the problem's technically fixed. But what about making sure it stays fixed and the rest of the organization learns? D7.
Crucial step, D7, prevent recurrence. This is about standardization. Updating your foundational documents, the FMEA, the control plan, making sure the lessons learned are built into things like layered process audits or maybe even training material.
If you skip D7,
You're basically setting yourself up to repeat the failure down the road when people forget or move on. Institutional memory is key.
and finally D8, team and individual recognition, but also closing it out with the customer, often through their specific portals. That seems like a whole other challenge.
It is, because each OEM has slightly different expectations and systems. You've got GM supply power, often focused on PRRs, problem reporting, and resolution.
What do they emphasize?
GM really pushes for rapid communication, daily updates, often using a fast response format showing progress, very tempo-driven.
Okay, good luck.
Then you have Ford with their global quality analysis system. They really emphasize the evidence trail and linking the 8D back. Specifically, they want lessons learned fed into their EAPQP system, the Electronic Advanced Product Quality Planning, to prevent similar issues in future designs, sort of future-proofing.
Interesting. What about Stellantis or VW?
Stellantis uses the Supplier Quality Portal, SQP. VW has KPMQS. Both demand really clear logic chains in your AD report. They want to see the connections, the proof of standardization very clearly.
And the German luxury brands.
Yeah.
Or Toyota.
Right. Mercedes-Benz has its QEC tool. BMW uses QMT. Toyota has SQAM. These often require, let's say, a higher level of analytical rigor in the documentation. You'll likely need to attach detailed lab reports, maybe formal governance records showing sign-offs, measurement systems analysis, or MSA data to back up your capability charts. Very data heavy.
So despite the different portals and acronyms, there's a common thread.
Absolutely. Clear, concise, evidence-based reporting wins. Show your work. Attach the data CPA charts, MSA results. Ambiguity gets penalized hard. They want confidence that the fix is real and systemic.
So wrapping this up, the big picture here isn't just about putting out fires.
Not at all. A world-class 8D process doesn't just solve today's crisis. It uses that crisis almost like an MRI for your organization. It helps you find and permanently fix a deeper weakness in your underlying system.
The defect is just the symptom then.
It is. The true failure wasn't just the part. It was the system that allowed it to happen, and then the other system failure that allowed it to escape.
So the question for you, the listener, isn't just, why did this part fail? It's also, why did our expensive quality firewall, our escape point, let it get through?
Exactly.
Which system in your own organization, maybe it's training, maybe maintenance, maybe process control, which system will you strengthen based on the next problem you inevitably have to solve?
All right, everyone. We're looking forward to your answers and experiences in the comments. Big thanks to Chris and Jane for today's great conversation. If you'd like more on 8D analysis, check out the 8D video on my channel. If you enjoyed this, don't forget to like the video and share it with your friends. To make sure you don't miss content like this, subscribe to the channel and turn on notifications. You can also steer our next episode by suggesting topics in the comments. Until the next video, bye for now.
You know, when it comes to the cars we drive, quality isn't just a nice to have. It's a whole rule book. And that rule book is really written in two parts. First, you've got ISO 9001. That's the universal foundation for quality in pretty much any industry you can think of. But then you've got IATF 16949, which is like the high-performance upgrade built specifically for the insane demands of the auto industry. And together, they create the system that makes sure the car in your driveway is safe, reliable, and actually built to last. And hey, you don't have to take my word for it. This one sentence, right from the standard's own introduction, it sums up the whole deal. IATF 16949 isn't a replacement for ISO 9001, it's a powerful supplement. The best way to think about it is this. ISO 9001 is the solid, reliable engine block. IATF 16949, that's the turbocharger you bolt on for maximum automotive performance. You just can't have one without the other. All right, so here's how we're going to break this down. We're going to start with that universal foundation, ISO 9001. Then we'll get into why the auto industry needed to level up and create its own upgrade. After that, we'll look at some of the really specific high-impact requirements that IATF 1699 adds to the mix. And finally, we'll connect all these factory standards to the car you actually drive every single day. First things first, to really get what makes the automotive standard so special, you have to understand the base it's built on. So let's do a quick dive into the global benchmark for quality management, ISO 9001. At its core, ISO 9001 is all about creating what's called a quality management system, or a QMS. Now, this is not just some dusty binder sitting on a shelf. Think of it as a living, breathing playbook for the entire company. It's the formal system that documents every process, every procedure, every responsibility, all to make sure a company can hit its quality goals consistently, time after time. So, what drives this whole system? It's something called the Plan, Do, Check, Act cycle. And it's a beautifully simple but really powerful loop. You plan what you're going to do. You do it, you check the results, and then you act on what you learned to make it even better the next time around. This constant cycle of improvement is the absolute heartbeat of ISO 9001. And that cycle is built on 7 key principles. These are like the philosophical pillars of quality. You've got an absolute obsession with the customer, making sure leadership is driving everything from the top, and this is a big one, a commitment to making decisions based on cold, hard data, not just guesswork. These principles create a solid foundation for any great QMS, no matter what industry you're in. Okay, so if ISO 9001 is so great, so universal, and so effective, why on earth did the auto industry feel like it needed more? I mean, what was missing that one of the most advanced manufacturing sectors in the world had to go and build something on top of it? Well, this standard didn't just pop up out of nowhere. The International Automotive Task Force, the IATF, they've been working on this for decades. It all started way back in 1999 with a simple goal: get all the different car makers and suppliers around the world onto the same page when it came to quality. What we have today is the result of all that work. A single, incredibly tough standard for the entire global supply chain. And this slide right here, this shows you the critical shift in thinking. See, ISO 9001 aims for overall improvement, which is a great goal for any business. But IATF 16949 gets laser focused. It's not just about improving, it's about preventing defects before they can ever happen. It's about aggressively hunting down and stamping out variation and waste. The goalposts move from, hey, let's do better, to let's get as close to perfect as we possibly can. So what does this upgrade actually look like on the factory floor? Let's get into the nitty-gritty and check out a few of the key mandatory requirements that IATF 16949 adds on top of that ISO 9001 foundation. First up, and this is a huge one, product safety. Now, of course, safety is kind of implied in ISO 9001. But IATF 16949 makes it an explicit, documented, non-negotiable process. It's not just a good idea anymore. It's a strict requirement to have formal systems in place to make sure your parts aren't a hazard to anyone. And we're not talking about a vague statement here. This thing is a web of interlocking requirements. It forces companies to have documented processes for everything, from identifying safety laws to having reaction plans ready to go. It requires special approvals for things like FMEAs, which is basically a deep dive analysis to find all the ways a part can fail before it's ever made. And it demands total traceability, so every single part can be tracked from the raw material to the finished car. Safety is woven right into the fabric of the process. All right, next up, let's talk about something the auto industry knows all too well: chaos. A single parts shortage or a factory shutdown can cause a massive ripple effect across the globe. IATF 1699 says you can't just cross your fingers and hope for the best. You have to plan for the worst. This is another huge level up from ISO 9001. The standard literally mandates that companies create and document contingency plans for all kinds of potential disasters. What's the plan if your main piece of equipment goes down? What happens if there's a cyber attack or a labor shortage? IATF forces companies to answer these really tough questions before a crisis hits, which builds a much, much more resilient supply chain for everyone. You know, at the end of the day, a car company is really just an assembler. The quality of that final car depends completely on the quality of thousands of parts from hundreds of different suppliers. IATF 6949 gets this, and it extends its reach way beyond the walls of just one factory. So what it does is mandate active supplier development. It's not enough for the big company to be certified. IATF 16949 requires them to have a program to guide their suppliers along this ladder, with the ultimate goal of getting them certified to the exact same tough standard. It's a massive, systematic effort to raise the quality of the entire automotive ecosystem, from the smallest supplier to the biggest brand. Okay, so we've been deep in the weeds with clauses, systems, and supply chains. But what does any of this actually mean for you, the person behind the wheel? How does all this complicated factory stuff translate from the assembly line to your daily drive? If there is one number that tells the whole story, it's this one, 0. The standard literally says that for certain kinds of inspections, we're talking simple pass/fail, is this part good or not? The only acceptable outcome is 0 defects. Not 1%, not 0.1%, 0. It's an incredibly powerful statement about the mindset behind this whole standard. So at the end of the day, what's the payoff for all this incredible rigor? Well, it all boils down to tangible benefits for all of us. You get increased product reliability, meaning fewer breakdowns and recalls. You get enhanced consumer safety, which is obvious. And the whole industry gets a more efficient, more robust global supply chain. It really is that simple. Every single clause, every audit, every contingency plan we've talked about, it's all another link in this massive chain of quality. A chain that stretches from a mine pulling raw materials out of the ground all the way to a vehicle you can trust your life with. The rigor in the supply chain leads directly to reliability on the road. But of course, this never stops. The standard is already tackling things like embedded software. But as our cars transform into rolling supercomputers, it leaves us with a really fascinating question. How do you guarantee quality and safety, not just in steel and plastic, but in millions and millions of lines of code? That, right there, is the next great frontier for automotive quality. Thanks for watching.
All right, let's get right into it. Welcome to this explainer. Look, if you're a manager in manufacturing or engineering, you absolutely know the dread of endless firefighting. It's exhausting, right? Well, today, we are walking through the ultimate blueprint to moving away from those temporary fixes and towards bulletproof, systemic problem solving. We're going to completely master the mechanics of the 8D system.
Okay, let's dive into this. Picture this scenario. It's a busy Tuesday on the production floor. Your phone rings. It's the customer, and they are furious. The brackets you shipped, they aren't fitting on their assembly line. Your heart rate immediately spikes. Now, imagine it's the exact same customer calling about the exact same error you thought you had completely fixed 3 months ago. Why does this keep happening? Well, the most dangerous illusion in the automotive and manufacturing world is thinking we solved the problem when, in reality, all you applied was a temporary Band-Aid.
So, to break that vicious cycle forever, here's our roadmap for today. First, crisis management and firewall. Second, forensic analysis for the root cause. Third, FMEA and digital poka-yoke. Fourth, chasing evidence with provocation tests. Fifth, systemic spread through Yoko 10. And finally, customer portals and success. Let's jump in. Section 1. Crisis management and firewall. Securing the perimeter. Our first phase covers steps D0 to D3 of the 8D process. When that angry customer calls, your very first reflex, literally within the first 60 seconds, has got to be stopping the bleed. Protecting the customer's production line is your absolute top priority. In the fast-paced automotive sector, this initial sprint is governed by the famous 1-5-20 rule. And remember, time is literally money here. You have exactly 1 day to contain the issue and establish a firewall. You've got 5 days to find and agree upon the root cause, and you have 20 days to implement and prove your permanent fix. Speed, combined with strict accuracy, is everything. And this brilliantly illustrates how the global 8D system is so much more than just a reporting chore or a document to fill out. It is a standardized, systematic approach to problem solving. By using this framework, you're speaking a common, evidence-based language with your client. When you structure your response this way, you establish immediate authority and show them right off the bat that you are handling this crisis like a true professional. So, what do those crucial first 24 hours actually look like? First things first, you stop and protect the line. Then you clearly mark and isolate your dirty, suspected parts from your clean, verified parts, just to make sure absolutely nothing gets mixed up. You must establish a clean point and prove it with hard records. But here's the critical step that teams skip way too often. You must run a gauge R&R, or measurement system analysis. Think about it. If you can't trust your measurement tools, your entire investigation is going to collapse. You have to verify your gauges before making any assumptions at all about the data. Section 2. Forensic Analysis, Root Cause, the true heart of 8D. All right, once that firewall is up, we transition into step D4. Treat this like an urgent forensic investigation to hunt down the silent killers operating inside your production line. To do this professionally, you combine Pareto analysis to pinpoint your most critical defects with the 5W1H method. Asking who, what, when, where, why, and how. We map this out using the three-legged 5 whys and Ishikawa or Fishbone diagrams. You can't just ask why the defect happened once and call it a day. You need a dedicated 5 whys analysis for the occurrence, the technical reason it broke, a separate one for the escape, why your quality assurance totally missed it, and a third for the systemic root cause, why the management or planning system allowed this flaw to even exist. Missing even one of these legs means the problem is absolutely coming back. So the crucial point is this: never ever accept operator error as a root cause. Seriously, it's a lazy excuse and nothing more than a temporary band-aid. True professionals are always hunting for the systemic gap, the permanent surgery. If an operator made a mistake, why did the system allow them to make it? Why wasn't there a physical safeguard in place? Finding that systemic gap is what actually prevents the defect from ever being reborn. Before we can even think about moving on from D4, you must ruthlessly evaluate your findings against rigorous control questions. You have to ask your team, does the proposed root cause completely and factually explain the defect's occurrence based on the actual data we collected? And you have to physically verify this on the line with on-off testing. That means intentionally triggering the defect to prove beyond a shadow of a doubt that you found the actual cause. Unverified theories simply have no place in an 8D report.
Section 3. FMEA and Digital Poka-yoke. Eliminating the chance of failure.
Now we shift gears into DeFi. This is where managers have to use risk-based decision-making. We update our FMEA files to reduce systemic risks based on solid data, not just wild guesses. We aren't just grabbing the cheapest or fastest option here. We evaluate our choices based on their mistake-proofing strength. This brings us to the brilliant philosophy of Poka-yoke, or mistake-proofing. The goal isn't to put up a sign telling the operator to be more careful. The goal is to build a system that physically protects against human error, using digital sensors, interlocks, and automation that make it literally impossible to produce or pass on a defective part.
Now, what's really interesting about this slide is this real-world example. Imagine a perfect 10mm shaft hole that keeps slipping down to 9.80mm. The root cause? Uncontrolled coolant concentration in tool wear. The DeFi solution wasn't a warning label, no, it was a level 3 Poka-yoke system. They installed an automated coolant mixer and an interlocking tool life counter. When that tool reaches the end of its life, the machine physically halts production before a single bad part can be made. It catches the error right at birth. That's a real game changer.
Section 4. Chasing evidence. Provocation tests. Validating the cure.
Selecting the right action is great, but it's not enough. We now move to D6. Listen, the automotive world does not care what you say you did. It only cares what you can prove with statistical stability. You have to validate the cure with hard evidence in the field to ensure errors are systemically blocked. We do this through a provocation test, sometimes called a rabbit part inspection. You essentially act as a saboteur and maliciously manipulate the system. In our shaft hole example, you'd intentionally install a worn tool or manually max out the life counter. Then you step back and watch. Does the new Poka-yoke interlock instantly halt the machine? If it stops that defect dead in its tracks, you've proven your technological armor actually works.
Section 5. Systemic Spread, Yoko 10. Future-proofing the organization. Once it's proven, we introduce the absolutely crucial D7 step. You have to ask yourself, is this same silent killer hiding in other machines on the floor? Or worse, in sister factories around the globe? Fixing one machine is a good start, but it's not enough to future-proof the organization. This is where we apply Yoko 10, the systematic horizontal spreading of a confirmed solution. Instead of just blaming operator error, you close the systemic gap everywhere. You take that automated coolant mixer and that tool life counter, and you make them the new corporate standard across all similar production lines. This is how a world-class factory evolves. You literally use today's defects to build true organizational muscle for tomorrow.
And of course, you have to document this new fortress. Under strict IATF and VDA standards, you must reevaluate your FMEA risk scores for occurrence and detection. You have to double-check if your shiny new automated systems accidentally introduced any new failure modes. You revise your control plans with digital precision, and you feed all these lessons directly into the APQP, the new product launch process.
Basically, the pain of this error must be permanently etched into your corporate memory.
Section 6. Customer portals and success. Closing the loop officially.
Let's move to and see how this builds into phase D8. An 8D process isn't over just because you fired off an email. It's only truly over when the customer's portal officially says, accepted. It is a highly disciplined, rigorous closure. OEM portals are incredibly strict, whether it's Ford's FOSN, Mercedes' QEC, VW's KPMQS, or Tesla's SCAR, you must prepare your evidence packages through the strict lens of an auditor. They demand comprehensive evidence, updated control plans, and often top-level plant manager approval before they will even think about closing a file. They want to see exactly how you close that systemic gap, and they want a one-page lessons learned card shared across your team. Plus, D8 is where you officially recognize and appreciate the disciplined teamwork of the maintenance staff and operators who made the success possible. Celebrate the win.
I want to leave you with this really powerful thought straight from the automotive trenches. Experiencing an error once is an experience, but allowing the same error to be reborn in a new project is a systemic failure. That right there is the true philosophy of continuous improvement.
So, as we wrap up this explainer, I have a challenge for you. Take this blueprint back to your factory floor today. Look at the absolute most frustrating recurring defect on your line and ask yourself, is your next fix going to be just another Band-Aid? Or are you finally going to step up and perform the surgery? Thanks for focusing in with me, and I'll catch you on the next explainer.
Okay, let's unpack this. Have you ever felt like you're just constantly putting out fires? Solving the same problems over and over again?
Oh, absolutely. Or wondering why a really good idea just doesn't seem to stick.
Exactly. If that sounds familiar, well, you're definitely not alone. Today, we're taking a real deep dive into the world of sustainable quality, true efficiency, and how to genuinely solve problems, not just, patch up the symptoms.
Right, getting to the root of it.
Yeah. And our sources for this journey, they're packed with some crucial frameworks, everything from lean and Kaizen
The classics.
to the hidden costs of poor quality, which we'll get into, and a deceptively simple technique that's incredibly powerful for root cause analysis. So our mission today is pretty clear. We want to equip you with insights to not just spot problems, but to actually build robust systems that prevent them in the first place. That leads to genuine efficiency and, let's be honest, probably a lot more satisfaction.
Definitely more satisfaction. What's fascinating here, I think, is that while a lot of these concepts, they started in manufacturing.
Right, you hear about Toyota and places like that.
Exactly. But their core principles are just incredibly versatile. They really offer a blueprint for excellence in pretty much any process, any field, even just in our daily lives, honestly. So we'll be sort of guiding you through these foundational philosophies, looking at some specific, really actionable techniques, and then hitting that critical financial perspective, how poor quality can just silently eat away at value.
Okay, let's dive in. So, our sources lay out this really powerful idea, almost like an equation. Lean manufacturing plus Kaizen equals sustainable quality. How does that fundamentally shift things from, say, a more traditional view of quality?
That's a great starting point because it completely reframes the whole concept. Traditionally, quality was often seen as something you check at the end.
The inspection step.
The final inspection, exactly.
Yeah.
But if we look at this equation, lean plus Kaizen, it means quality isn't just about the final thing the customer gets. It's something that's built into every single stage, every step of the process.
So it's proactive.
Completely proactive. Preventative, not reactive.
So it's not just about speed then, or even just making things cheaper necessarily. It sounds like it's about a smarter kind of efficiency.
Exactly. Smart efficiency is a good way to put it. Lean, at its core, it's about maximizing the value for the customer while simultaneously minimizing waste.
Right.
And waste can be anything, time, materials, effort.
Right, wasted movement, all that.
All of it. And then you bring in Kaizen, which it's Japanese for change for the better, and that emphasizes continuous incremental improvement, just small, ongoing adjustments.
Little tweaks adding up.
Precisely. So when you combine those two powerful ideas, you start to create a culture where quality becomes almost automatic. Waste gets systematically squeezed out. Perfection isn't some static goal you hit once, it's this ongoing journey.
Okay, so no more patchwork solutions then. You're actually fixing the foundation.
Exactly. You're fundamentally changing how things are done from the ground up. No more Band-Aids.
That sounds, well, incredibly powerful for transforming pretty much any process. Our sources dig into 5 fundamental approaches, almost like 5 pillars, that really help achieve the sustainable quality. What's in this toolkit for us?
It is a very practical toolkit, yeah. Each
piece gives you a different lens, a different strategy for improvement.
Okay.
So first up, we have Gemba. This is maybe the most fundamental. You literally go to the actual place where the work happens, where the problem is occurring.
Get out of the office.
Exactly. Go see it. You observe the flow. You talk to the people doing the work every single day. It's about direct engagement with the reality, not just reading reports or making assumptions. One source put it really well. It's about directly touching the real problems. You're seeing it, hearing it, feeling it right where it happens.
Getting your boots dirty, as they say. Okay, what's next in the toolkit?
Next is Poka-yoke. It basically translates to error-proofing.
Error-proofing.
Yeah. Think simple, clever solutions designed to prevent mistakes before they can even happen. Like, a USB plug only fitting one way.
Ah, right. Physical constraints.
Exactly. There's systematic actions you can implement. And importantly, they don't always need big investments. A really compelling insight here is that Poka-yoke isn't just preventing errors, it makes waste impossible to hide.
Okay.
Imagine this like a simple jig on an assembly line that only lets parts fit the right way. Maybe it cuts assembly errors by, say, 80% overnight. Tiny investment, huge return.
Wow.
You integrate these into the process, solve problems before they start. It leads to sustainable quality because you're literally designing failure out of the system.
Designing failure out. I like that phrasing. That's brilliant. What about balancing things out, fluctuations in demand?
Good question. That brings us to the third approach, Haijunka. It's about production leveling.
Haijunka. Okay.
Yeah, it's all about balancing your production against the ups and downs of customer demand. When you do this well, you dramatically reduce bottlenecks, you increase flexibility.
So you're not scrambling when orders spike or idle when they dip.
Precisely. Think about a factory trying to make everything at once during a peak, then sitting quiet. Haijunka smooths that all out. You work with lower but consistent stock levels. This also means if you do have an issue, your scrap costs are minimized because you're not holding tons of potentially bad inventory.
Right, less exposure.
Exactly. And the result is this great combination. Low cost, high quality, efficient production, and ultimately happier customers because things are more predictable. It's about achieving a steady, predictable flow.
Makes sense. Keep things running smoothly. But what about when errors do happen? Because, they still might.
They still might, absolutely. And that's where Jigoku comes in. It's often described as automation with a human touch. Or maybe more directly, the idea of stopping production immediately when an error occurs.
Stop the line.
Stop the line, essentially. Instead of letting a faulty product continue down and maybe even reach a customer, you have systems in place, things like and-on systems, maybe light flashes or an alarm sounds, or in-place quality applications. These automatically halt production the moment an error is detected. The core idea here isn't just quality control after the fact. It's quality at the process level.
So you catch it right then and there.
Right then and there. It lets the team focus on the root cause immediately. This means fewer complaints down the line, lower scrap costs, more efficient production overall, and better customer satisfaction because you're fixing errors quickly where they happen and stopping them from spreading.
So it's not just about machines being automated, but it's empowering the people to react instantly when the system flags an issue.
That's a perfect way to put it. The system has the intelligence to spot the problem, and the human operator has the immediate power and responsibility to investigate and fix the underlying cause.
Got it. And the last one.
And finally, we have the famous 5S. It stands for sort, set in order, shine, standardize, and sustain.
Ah, yes. 5S workplace organization.
Exactly. It's all about creating an organized, standardized workspace or production site.
Yeah.
Our sources really emphasize that the order of the production site is perhaps the most fundamental starting point.
Why is that so fundamental?
Because when your workspace is orderly, clean, free from clutter, problems just become visible. Areas for improvement become clear. With 5S, it's not just about being tidy for tidiness' sake. It's about making waste, inefficiency, and problems impossible to hide.
Okay, so they stand out more.
They stand out dramatically. The sources note that when order is established, many problems seem to almost solve themselves, or they become so glaringly obvious they're practically screaming for attention. It leaves you to focus on the more strategic adjustments. Plus, it really transforms the work culture along with the quality.
So a clean, organized space isn't just, nice to work in. It's actually a powerful problem-solving tool itself. I like that connection.
It really is.
Okay, now let's shift gears a bit and talk about something that can silently, really drain an organization's resources. Our sources bring up a concept that's often overlooked, or at least underestimated, the cost of poor quality. COPQ.
COPQ.
They use this vivid iceberg analogy. You know, the things you see like scrap costs or warranty claims, that's just the visible tip. What's really lurking under the surface of that iceberg?
Ah, the iceberg. It's such a good analogy because COPQ is this much broader structure that's just quietly eroding profitability. When we break it down, there are really two main categories of these costs. First, you've got the visible or direct costs.
The obvious stuff.
The obvious stuff, yeah. The ones we tend to think of first. That's your scrap costs for products you just can't use, the rework costs for fixing faulty ones you can salvage, and then all the costs after it leaves your door, customer returns, warranty claims, screening, repairs. These are tangible, usually easier to track on a spreadsheet. But then, and this is where it gets really insidious, as you said, we have the invisible or indirect costs. These are the ones that truly sneak up on you.
The hidden part of the iceberg.
The massive hidden part.
Yeah.
This includes things like unplanned downtime, because a machine went down due to a quality issue, speed losses on the line, just general low production efficiency because you're dealing with non-conforming products. You also see dips in key metrics like OEE, overall equipment effectiveness.
Right, the big manufacturer metric.
Exactly. And OLE, overall labor effectiveness, OPE, overall process effectiveness, these drop because of all the unplanned things you have to deal with poor quality. And maybe the sneakiest of all, opportunity costs.
Opportunity costs, like what?
Like potential sales you lost because your reputation for quality isn't great, or projects you couldn't take on because your resources were tied up fixing problems. The key insight from our sources here is really powerful. The invisible part of the cost of poor quality often has the potential to be larger than the visible part.
Wow. That's actually incredible. The hidden costs can outweigh the ones you actually track easily. But if they're so hidden, how did the sources suggest we even start to, well, unearth them? And why is it so crucial to actually put a number on COPQ? Why not just be aware it exists?
Well, being aware is the first step, but putting a number on it gives it power. You start by really mapping out your process, identifying every single touch point where an error could occur. Then you meticulously track the time lost, materials wasted, the extra effort expended at each of those points.
That sounds like a lot of work.
It can be, but this is where that Gemba walk we talked about becomes invaluable again. Seeing the process firsthand often reveals these hidden drains much better than just looking at data. Now, calculating COPQ is critical for several strategic reasons.
Okay.
First, it lets you accurately calculate the true profitability of your projects or products. It gives you a much clearer picture of your financial health. Second, it helps you prioritize your improvement efforts correctly. You focus on the things causing the biggest financial drain, not just the loudest complaints.
Makes sense. Follow the money.
Follow the money. Third, you can calculate the ROI, the return on investment, for any improvements you're proposing. If you want to invest in, say, error proofing, you can show exactly how much COPQ it will eliminate.
Ah, building the business case.
Exactly. And that leads to the fourth point. Having these clear financial figures helps you get that necessary management support. You need budget for quality initiatives. Showing the cost of not doing it, the QOPQ, is incredibly persuasive. It turns quality from this sort of subjective nice-to-have into a measurable financial imperative.
That really reframes how you think about investing in quality, doesn't it? It's not a cost center. It's preventing much larger hidden costs.
Precisely. It's an investment with a clear return.
Okay, brilliant. Now let's tackle that common frustration. I think probably everyone listening has felt this. You think you've solved a problem, you put a fix in place, and then bam. Weeks or months later, it pops right back up again.
The whack-a-mole problem.
Exactly. It feels like whack-a-mole. The real challenge often isn't just spotting the problem. It's truly understanding why it's happening in the first place. And this is where another fantastic tool comes in, one that sounds almost too simple. The 5 whys technique.
Yes, the 5 whys. What's really striking about it is just how profound its impact can be despite its sheer simplicity. The process is straightforward. When a problem occurs, you ask why.
Okay.
Then, whatever the answer is, you ask why about that answer. And you keep going, usually about 5 times, or until you get to a point where asking why, again, doesn't yield a useful answer. Or, ideally, you reach a fundamental systemic cause you can actually address.
Right.
It sounds basic, but it's really a disciplined way of thinking, not just a quick Q&A.
It sounds almost like being a detective, you know? Always asking just one more question, but for organizational problems.
Yeah.
What are the real payoffs here? Why go through those 5 layers?
The payoffs are truly transformative, really. First, it forces you, absolutely forces you, to get past the obvious, superficial answers. The first why often points to something easy, like, oh, human error or the equipment failed.
The immediate symptom.
Exactly. But the last why, if you do it right, almost always reveals deeper systemic issues. Things like gaps in training, procedures that aren't adequate, maybe even fundamental design flaws in the process or product itself.
Ah, so you get to the real root cause.
The real root cause. Second, and this is crucial, problems stay solved. When you address these real systemic causes, you prevent the problem from coming back. Quick fixes, those Band-Aids we talked about, they might make the immediate pain go away, maybe make your monthly report look okay.
Right.
But they don't stop it from happening again. 5 Whys forces you to dig deeper for a permanent solution. And third, and I've seen this happen so many times, the team starts thinking differently. Once people learn this discipline of questioning beyond the surface, they develop a much more proactive mindset. They start asking why about things before they become problems. It helps catch potential issues earlier. It really cultivates a culture of genuine problem prevention, not just reaction.
That shift in mindset sounds incredibly valuable. But, you know, for a technique that seems so simple on the surface, there must be a key to doing it right. It can't just be asking any 5 whys, can it?
No, absolutely not. Its success really hinges on discipline. First, you need the right people involved, people who actually know the process inside and out, who work with it daily, or who have access to the relevant data.
Get the experts in the room.
Get the real experts in the room. Second, every single answer, every step of the way must be based on facts and data, not on assumptions, opinions, or just gut feelings.
Stick to what you know.
Stick to what you can verify. And third, critically, you mustn't stop asking why until you find something that can be systematically changed. The goal isn't just to find a reason, it's to find an actionable, system-level change you can implement.
That's the key, finding something you can actually fix in the system.
Precisely. And here's some really crucial advice that came through in our sources. Avoid the blame game. When problems occur, don't point fingers at individuals.
That's tempting sometimes, though.
It is tempting, but it's counterproductive. Pointing fingers usually means the real underlying system issues remain unaddressed, and guess what? They'll just keep happening, maybe with a different person next time.
Right.
So instead of blaming people, the focus has to be on fixing the systems and the processes that allowed the problem to occur in the first place. That's the fundamental shift.
Focus on the process, not the person.
Exactly. The real value here isn't just solving today's problem, though that's important. It's building the capability, the muscle memory within the organization to prevent tomorrow's problems. And as a side benefit, it also provides excellent documentation for things like audits. It shows you've done a thorough investigation and you're proactive about quality.
Okay, so wrapping this up then, what does this all mean for you, the listener? We've journeyed through quite a bit here, from the core philosophy of building quality right from the start with Lean and Kaizen. We explored those 5 powerful tools for process transformation like Gemba, Pokeyoke, 5S. We uncovered those often hidden, really significant costs of poor quality, the CPQ iceberg.
Right, the hidden part.
And we learned how to truly get to the root of problems and make them stay solved using the 5 whys. These aren't just, abstract management theories. They are practical, actionable tools. You can use them to drive efficiency and excellence in pretty much any domain you can think of: factory, office, even your own personal projects.
Yeah, and if we just zoom out for a final thought here, these really aren't just industrial methodologies anymore. They're fundamentally frameworks for critical thinking, for continuous improvement. And that applies to any system, any project, even our own personal habits, really. Which kind of begs an important question, doesn't it? Where in your own life or in your own work could you maybe apply a quick Gemba walk just to really see a problem firsthand? Or where could you ask why 5 times to uncover a root cause you've maybe been overlooking instead of just, patching up that same symptom again and again?
That's a great question to leave people with. Think about that. The power to transform processes, save costs, and genuinely solve problems, it really is at your fingertips, starting with some of these insights we've discussed. Until next time, keep diving deep.